Let's take a look at the mathematical foundations of machine learning. Much of what AI is based on is machine learning. Machine learning is statistical modeling. So this should sound somewhat familiar. It's statistics and probability are very closely related, and we covered probability in week 3. Now, if you've seen a chart like this, a graph like this, and you understand how it works, then I can assure you, you should have no problem understanding the mathematical foundations of machine learning. So let's take a look at this. So you can see here that we've got a list of numbers. So we have this list right here, and that is plotted here on the x-axis. And it's plotted in correlation to these numbers here. And those numbers are our y-axis. So if we take a vector here, or a pair of these two numbers, which we could write in what's called vector format, is square brackets, and we do usually x first, comma, and then y. And you might remember all of this from algebra in high school, algebra 1 or 2. We can take these two numbers and we can plot it. So we can find here, we can look, here's 10, here's 20, so 15 is in the middle somewhere. So here's 16, let's say, and we plot up until we get to this. So we found 16. We're going to plot till we get to 5,825 roughly. Well, that is, oh, looky there. That is, let me do a better circle there. That little dot right here. Sure enough, they've plotted that. So we can see if we go then through all these other numbers that all of these pairs of numbers here have been plotted, right, as these black dots. Okay, so that's understandable. And there's an indication here, and we can see in the chart that there is a correlation between the two pairs of numbers. So there's some sort of relationship, some sort of correlation and this one looks like as we go up higher numbers on the x-axis, we're seeing an increase on the y-axis. Now, if we just had the dots there, we might not notice it. I mean, we probably would, it's pretty obvious, but sometimes you'll see charts with a bunch of dots and it's really hard to see if there's any correlation or trend. And so what will happen then is that these statisticians will come in and they'll do some sort of math, right? And that's a function. So some sort of mathematical equation, which we call a function. And, again, you may remember this, you do it so that there comes out to be a straight line. You can plot that, you can formalize that in a mathematical function in such a way that any x, right, any number on the x-axis that you input will be fed through that mathematical equation, and it will spit out the y-axis that you need to find the correct spot that will be actually on this line. So that's the concept here. Now let's notice a few things here. I'm going to clear this again. Notice, so we had these observations, and what are these numbers coming from? Well, they could come from a bunch of things. These happen to be some that I pulled from the internet, and it was an example here that snow days and road incidents, like accidents on the road. And this may not make much sense to somebody living in Florida, but let's just say instead of snow days, it's days with bad weather. So you can see this correlation, right? The more on the x-axis, the more bad weather days there are, the more road incidences we have. Well, that makes sense. We can see how that would make sense. And sure enough, here's the trend. Here's the line. We got the mathematical formula. But to get that line, we had to plot these actual. So, maybe it's the past 10 years, and every year we count the number of bad weather days and then count the number of road incidents in that year, and we have a correlation. So in this this year here, there were, well, that one corresponds to this line here. There were 59 bad weather days and 11,449, right? So if we mapped it there. It's going to be at 11,449, and this is going to be down here at 59. And we plotted all of them. So then that was 1 year. This was another year. Here's another year, and there's 10 years there. Well, that's what happened. That's our observations that we have of the past. And so this line here, what is this? Notice that except for right here, in here, I'll clear this again so you can see, or let me back up a little bit so you can be a little bit clearer. You'll notice that that line, which shows this trend that if you know how many, is basically saying, we can see if you have this many bad weather days, you're going to have these many accidents on the road. But it's showing the trend, and yet there's only this one instance where the dot actually that's plotted actually falls on the line. Now, why is that? And how do we get there? Well, it's showing a trend, again, showing this trend that we can see very clearly. That's one thing. The reason only one of those dots is on the line is because the trend isn't trying to get as many dots as possible to fall on this line, although you would think that's what you would do, like get as many as possible, and that will show us the trend. Instead, there's some math going on here, which simply put is if we measure the distances from each of these dots to the line, and we can try a bunch of different lines, and we measure the distance. We actually measure it in a square distance, so we actually do it that way. But anyhow, that's not important. Let's just do it simply. If you measure the distance, then this line that's been plotted here, if you add up all the distances, this is the line that will give you the minimum number. So if you move the line up and down and then we added the distance, it would be a larger number. So this is not matching as many dots. It's the line that is the minimum or optimal minimum distance from all of those dots. All right, so you do some math to figure that out. So that's how you do it. And that's how we get our trend. Okay, if you can understand all of that, then you're good to go, really. So that's the basic idea of how machine learning works. With this slight change that now we have the trend of this pattern that we've seen in the past, and now we have, oh, let's say there's a new year coming up and you're in charge of the Department of Transportation in your state, and you want to know how many people you should hire or how many emergency vehicles you should prepare or nurses or whatever to prepare for these road incidents. And what are you going to do? Well, you don't know what's going to happen in the future, but let's say you could go to the almanac, and let's say the almanac is accurate and it tells you, well, this year, and let's say 2026, next year, we're going to plan for next year, there is going to be 50 road incidents, or 50 bad days. Sorry, they're going to be the x-axis. There's going to be 50 bad weather days. Say, okay, if I have 50 bad weather days and I use this line, this trend here, then I should be able to figure out how many road incidents I should prepare for. So I just plot up here, up, 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 until I get to where it hits the line. And that right there, actually use my little X tool. There it is right there. Isn't it pretty? There you go. There we go. Nice little X. Perfect little X. That I can then plot from there over to, it's not a very straight line, but over to the y-axis, and this lands, as it happens, right at 10,000 road incidents. So now I'm going to say, okay, that we expect to have 50 bad weather days, so we are going to predict that we need to prepare and budget for 10,000 road incidents. So what have we done here? We've used the pattern that we've observed in the past, observations from the past. We've turned that into this trend or prediction, or this line of trends. And now we're assuming that this line is going to extend and be true for the future. And based on that, then we get some data and we make a prediction. And that is how AI works. All right, so you might ask, well, how do we do this with language? How does it relate with language? Well, let's look at this. Let's just change this a little bit. Let's say These numbers are not road incidents. Let's say we have a corpus of text, of running text, and we count up all the parts of speech. Let's make this parts of speech. So I'll put POS. And there's 10 different parts of speech in this language that we're working with, parts of speech. And there, I don't know, it doesn't matter which one is which, but the first one has 5,825 of that part of speech in this corpus of text. The next one is 11,427. Nouns, verbs, adjectives, etc. We could draw a chart like this by plotting how many parts of speech there are. But to do this is actually up here. This is actually the number of each part of speech. This right here is going to be our parts of speech labels. And you'll notice there's numbers here, right? Why numbers? I mean, part of speeches are not numbers. And we've just put random numbers there. We assign random numbers. Why do we do that? Is there something special about 16? And let's say this is the verb. No. We just chose a random number here. You could do some tinkering to make it work out nicely, as we'll see in this chart. But this 16 doesn't mean that there's something inherent about verbs that is 16. It's an identification. It's similar to how if you are legally allowed to work in the US, you have a social security number. Mine starts with 4, but that doesn't mean I'm the, I don't know, 40,000, 400,000 person. It's just an identification. That number is randomly assigned to me. There's nothing inherent about me or the value or the amount of me that's related to that number. So why assign numbers? Well, this cool thing, if we assign something, if we use numbers to identify something, we can use those numbers to plot the information into a space. So in this case, a 3D space, we can plot them on a number line. And once you plot it on a number line and you have numbers, you can do math with them. You can do really cool stuff once you can do math. So it doesn't matter whether or not there is 16 of something, 16 verbs, or 16 as something inherent. It's just a random number that we've assigned. But it allows us to plot them on a number line. And once you plot them on a number line, you can do math. And so you can do a bunch of cool things with math. So that's what's going on. So we're just going to randomly assign, right? We don't even care what the part of speech label is. That's actually not important. The computer doesn't know. It just knows it's a number. The number represents information. And we just, kind of did this cleverly so that it just so happens that the number that was assigned, where's 16, like right here, is the one with the fewest instances of that part of speech in the text, and the one that has the highest randomly assigned number, 59, it also happens to be the part of speech that's the most frequent. That's just, we did something clever there to make that happen. Okay, so now let's do the predictions here. Well, what would be a somewhat realistic situation, possibly? Well, let's say it's a language you've never worked with, you have this corpus of text, you did all the counting of the parts of speech, and then your coworker also did counting of a different corpus of text, maybe roughly the same size, but they left the tags off, right? And you forgot they just gave you the numbers on it. And so you don't actually know which part of speech they are, you just have the numbers for them. And let's say there's one category that has 12,000 of that particular part of speech in this corpus of text in the second one, but you don't know the language. You can't look at it and say, oh yeah, those are nouns or verbs. You just know it is some parts of speech, and you have to figure out now which one it is, right? Which box would it fall in here? Well, you can look at it and you say, well, my corpus that I did the counting on here is roughly the same size, has roughly the same number of words as my coworker's corpus. So he left, he didn't give us the information. But his corpus that he counted is roughly the same size. So I'm going to make a prediction. That's my context, right? I've got my counting of the number, both in mine and in his. And I've got the context, which is, so this is a phenomenon, how many instances of part of speech, and the context would be this corpus that is roughly the same size. And so I'm going to assume, I'm going to make this big assumption that all parts of speech occur at the same proportion of frequency in any text. So that means if the corpus of text is roughly the same size, I should see the amount of each, right? The number of each part of speech here, for example, that one in a corpus of roughly the same size should be roughly the same number, should be the same number of this, and this one should also have pretty much the same number, and this one as well. This seems like a big assumption. Turns out it actually works pretty well in English. You can actually make that assumption and it works pretty well. You're going to see the same, roughly the same proportion of verbs, roughly the same proportion of nouns, especially if it's the same genre of text. All right, so we're going to make that assumption then to figure out which part of speech this is. How are we going to do that? Well, there's one quick thing, right? To notice the number we have here is on the y-axis, and just a quick note there. What we had before was this is a normal way of writing it. You up here, right? You feed in the x and you get out the y, but it really doesn't matter. You can go both ways. You can feed in the y, which is what you have, and you should get out the x. You just make your formula work that way. So that's just a little thing to note. Hopefully you weren't confused by that. Okay, so with that formula then ready for us and this trend line and our numbers there, we now have this assignment to figure out which of these parts of speech, boxes, categories, does this group of words with the 12,000 instances belong to. So we just do the same thing we did before. We're going to find 12,000 on the y-axis, which is here, and we're going to go across till we get to the x-axis, and we're going to put an x there. And that's the part of speech. Wait a second, there's no part of speech there, right? We extend the line, there's no dot there. What's going on? How can we, it didn't land in any of them. And you can't be somewhere in between nouns and verbs. In a running text, you're either a noun or a verb or an adjective. That's how language works. These are categories, they're not continuous. Like incidents on the road and snow days. So how in the world can we use this? Well, stop and think about this. If you had to assign this category that you've plotted here, or this group of words, right? If you had to assign it to some part of speech, which one would you choose, right? So each of these, we plotted the parts of speech here. It needs to belong to one of these dots. Which one would you choose? Now think about that for a second. If you said, well, I would just measure the distance to all the possible parts of speech and choose the one that is closest, and then say that's the one it belongs to, you would be very smart because that is exactly what happens here. These machine learning models, they get some information, they make a guess, and then they do this measuring. It's called Euclidean distance or Hamming distance. It's a way to measure. It's basically we're thinking of these pieces of information as spots in a actual space, and just like you would measure the distance between your house and the road, for example, you can measure the distance between the information that you have, the new information you have, and the categories you're trying to predict. So we just eyeball it here. I'm not going to actually do the math here, but I'm pretty sure to me it looks like this one right here is the closest category. So that's the one we're going to choose. Let's say that this category that has 12,000 instances in this corpus that's plotted here on the line is closest to this part of speech here. And this part of speech, let's see, we're going to plot that down to the x-axis down here, and that looks like that's about 59. So that means 12,000 group of 12,000 words that belong to the same part of speech. We're going to say it belongs to the 59 part of speech category. I don't know what that is. Let's say it's very frequent. Verbs tend to be pretty frequent, so we'll just say maybe that's verbs there.